We know that the photoelectric effect is a phenomenon of the emission of electrons by a metal surface after absorbing light energy. The electrons thus emitted are called photoelectrons. The history of the photoelectric effect dates back to 1887, when this phenomenon was accidentally discovered by Heinrich Hertz. Hertz was investigating the production and reception of electromagnetic EM waves through an experimental setup. His setup consisted of a spark gap transmitter and a receiver in the form of a coil with the spark gap placed at some distance from the transmitter. When a spark occurs in the spark gap of the transmitter, it produces electromagnetic waves, which are detected by the receiver, indicated by the sparking in its gap. To be able to see the spark better, he had placed the apparatus in a darkened box. However, to his surprise, Hertz observed that the maximum length of the spark was reduced when in the box. When he placed a glass panel between the source of the electromagnetic waves and the receiver, the glass panel absorbed ultraviolet radiation. This radiation had helped the electrons jump across the gap. Hence, the spark was longer before the glass panel was placed. This was due to the photoelectric effect. Because when light fell on the surface, some of the electrons on the surface absorbed enough energy from the incident radiation to overcome the attractive force of the positive ions of the material of the surface. An electron is able to escape from the metal surface only when its kinetic energy is sufficient to overcome the electrostatic attractive force. When the light was removed, the length of the spark decreased as there were no electrons being emitted by the surface. Moreover, he observed that there was no decrease in the length of the spark when he substituted glass with quartz, as quartz does not absorb UV radiation. This was one of the initial recorded observations of the photoelectric effect. During the period 1886 and 1902, two physicists, Wilhelm Holwachs and Philip Lenard, carried out a thorough investigation of the photoelectric effect phenomenon. Lenard conducted an experiment in which he placed two electrodes, an emitter or cathode, and a collector plate inside an evacuated glass tube. He connected the collector plate to the cathode by a wire through a sensitive ammeter to measure any current in the circuit. He then allowed ultraviolet radiation to fall on the cathode or emitter plate. As soon as the ultraviolet radiation fell on the cathode, a current flowed in the circuit, which was measured by the ammeter. He also observed that as soon as the ultraviolet radiation was stopped, the current also stopped flowing in the circuit. It was evident from the experiment that as soon as ultraviolet radiation falls on a cathode plate, it emits electrons. These electrons are attracted by the positive collector plate and start flowing towards the collector plate. As a result of the flow of electrons inside the glass tube, an electric current is observed in the external circuit. Further studies of this phenomenon were carried out by Wilhelm Holwachs through a very simple experiment. He mounted a clean, circular, negatively charged zinc plate on an insulating stand and connected it by a wire. to a gold leaf electroscope. He observed that when ultraviolet radiation was incident on the negatively charged zinc plate, it lost its charge. Also, he repeated the experiment by replacing the negatively charged zinc plate with an uncharged zinc plate. The uncharged zinc plate became positively charged when ultraviolet radiation was incident on it. Moreover, using a positively charged zinc plate in the same experimental setup further enhanced the positive charge of the already positive charged zinc plate. From the various observations of his experiment, Holwachs concluded that negatively charged particles were emitted from the zinc plate under the action of ultraviolet light. Holwachs and Lenard also observed that no electrons were emitted by the surface when the frequency of light was less than a certain minimum value. This minimum frequency of incident light below which no photoelectrons are liberated from the metal surface is known as the threshold frequency or work function. Threshold frequency depends on the nature of the metal surface. Certain metals such as zinc, cadmium, and magnesium respond only to ultraviolet light, as they have short wavelength and a high work function. Whereas some alkali metals such as lithium, sodium, potassium, calcium, and rubidium are sensitive even to visible light. Such metals which emit photoelectrons in visible light and have a very low work function are known as photosensitive substances. A solar panel can be used to produce electricity, and its working is based on the photoelectric effect. Let's learn about this through an experiment. Using the apparatus shown, let us study the experiment that explains the photoelectric effect. The apparatus consists of an evacuated glass or quartz tube T with a transparent quartz window W that permits radiation to pass through it. S is a source of monochromatic radiation. The evacuated tube consists of a photosensitive metal plate C, called the emitter plate or the cathode plate. This is similar to the functioning of the solar cells in a solar panel. The emitter plate C can be made of photosensitive metals like magnesium, zinc, and cadmium. These metals produce the photoelectric effect with ultraviolet radiation. However, if the source of light used is visible light, then the photoelectric effect is observed with metals like lithium, sodium, potassium, cesium, and rubidium. Another metal plate A, called the collector plate or the anode plate, is also sealed inside the evacuated tube. A battery B is connected to the emitter and collector plate to provide the potential difference through a commutator K, which is used to reverse the polarity of the cathode and the anode. The apparatus also consists of a rheostat RH, which can be used to adjust the potential difference applied between cathode and anode, and a microammeter A, which measures the photoelectric current in the external circuit. The emitter plate is now maintained at negative polarity and the collector at positive polarity using the commutator, so that the electrons emitted by the cathode can be collected by the collector or anode A. Monochromatic radiation from source S passes through the quartz window W and is incident on the photosensitive emitter plate C. The photosensitive emitter plate C starts emitting electrons. The potential difference between the cathode and the anode accelerates the electrons towards the collector plate, and hence this potential difference is now referred to as accelerating potential. The emitted electrons reach the collector, and when they flow in the external circuit, the resultant current, called the photoelectric current, is measured by the microammeter A. Using this experimental arrangement, let us now study the variation of photoelectric current when we vary the intensity of radiation, frequency of radiation, the applied potential difference between the plates, and the material of the emitter. Intensity of radiation is defined as the amount of energy incident on a unit area in a unit time. As you increase the intensity of light incident on the metal plate, you will notice that the resulting photoelectric current increases proportionally. This is because, as the intensity of light increases, the number of photons incident per second on the metal plate increases. This results in the number of emitted electrons increasing and hence increases the photoelectric current. Let us now study the effect of the applied potential difference on the photoelectric current. As you gradually increase the accelerating potential across the emitter and collector plates, you will notice that the current in the microammeter increases. We know that this happens due to an increase in the number of electrons that reach the collector plate per second. As the accelerating potential across the emitter and collector plates increases further, you will notice that the current in the microammeter reaches its maximum and remains constant. This maximum value of the current is called saturation current. Saturation current is a consequence of all the photoelectrons emitted by emitter plate C reaching the collector plate A. Now the polarity of the cathode and the anode are reversed. This potential builds a positive charge on the emitter plate that attracts the emitted electrons. The negative charge on the collector plate repels the emitted electrons. Hence, this potential is called retarding potential. As the retarding potential increases, you will observe a sharp decrease in the photoelectric current.